Thank you again. For those that were not in the previous talk, my name is Franz. I'm a development manager in MathWorks. I lead the signal processing team, signal and wavelet analysis team. And this is a great time to give the talk after the previous presentation so that I can take a little step back and talk a little bit more in detail about what is time frequency analysis and give you some insights into when do you choose which type of time frequency analysis. Why are there so many different transforms out there, and which one is the best one for what I'm doing? And today we just saw the audio engineer talk about MEL spectrograms and auditory type of time frequency analysis. So let's talk about all the different types of time frequency analysis out there. So the first thing I want to say is that I'll start with some motivation on why we need time frequency analysis. And if you're already convinced about the importance of this domain, great. But or if you become convinced today, the one thing that you have to be sure about is that there's no the time frequency transform. There's not such thing as the one. There's so many. And so it's a challenge, but it's also a great opportunity because you have all these flavors to choose from. So there are several techniques available, and I'm not going to be able to go through all of them, but at least I'll be able to talk about a couple of important ones, like the Fourier transform, the short-time Fourier transform, and the wavelet technique, which is the continuous wavelet transform. I'll also talk about reassignment techniques, especially synchro-squeezing, multi-resolution analysis, and then I'm going to go into time frequency for machine learning. Now, here I'm going to show you a very nice example that has me really excited. We just actually put it in our latest MATLAB, so you'll be able to follow up later on and see it. But I think that you're going to appreciate the importance of time frequency analysis when you see that example. All right, so in our typical courses in school, we always look at sorry, where am I? Yeah. At the typical courses, we see always, the time domain and the frequency domain separated. We talk about linear time invariant systems, and we talk about stationary signals. And so Fourier transform is enough for me, and I can go from the difference equation of the system to the transfer function of the system, right? And go back and forth between time and frequency. But we always keep separation between time and frequency in our courses. Now, think about music. Our auditory system is perfect at detecting both the time flow of music and the frequency flow of music, right? It's very natural for us to just think about the two things as one. And so, the multiple signals in the real world are just time frequency have time frequency content that needs to be analyzed together. So biology has no problem in figuring out time frequency transforms. However, mathematically, it's challenging. And the reason it's mathematically challenging is because there's no trivial way to define instantaneous frequency. Just think about this, instantaneous frequency. How do I detect instantaneous frequency? I need to observe a signal for a certain period of time. Okay, but if you're observing a signal from a certain period of time, then you're not doing an instantaneous observation. So there's this problem where you have this contradiction that is typical of time frequency analysis. Now, so the instantaneous frequency seems to be used mutually exclusive instantaneous frequency seems to be mutually exclusive from the actual instantaneous concept, all right? So the result is that there's no unique satisfactory way of describing a joint time frequency signal, but we can try. Okay, so to motivate a little bit why time frequency is important, here I have two representations of a signal that has 6 different tones, right? In the time domain, you can see that the tones come in pulses. I may be able to zoom in and look at the duration of the pulses, but I really can't figure out what's the frequency. Now, if I look at the power spectral density estimation, I can see 6 peaks in the spectrum. So I know that there are 6 tones, 6 different tones. However, I don't know where in time these tones happen. Now, if I look at the spectrogram or the short time Fourier transform magnitude, then I quickly see that there are various frequencies, and I can see the times at which these frequencies occur. And that's where time frequency becomes really useful, right? To detect events in frequency and in time. Now, many time frequency techniques derive their strengths and their limitations by the way they tile the time frequency plane, right? But before I expand on this, I want to show you the picture on the bottom here that shows this impulse in the time frequency domain. And this is an impossible transformation, right? There's no such thing as instantaneous time and instantaneous frequency in the same time frequency plane. So you can either have one impulse in the time or one impulse in frequency, but not in both, right? And the questions that arise are, each one of the different transforms has this unique or minimum resolution in each one of the variables, right? Either good resolution in frequency, good resolution in time. And the question is, what governs this resolution and why? So I'm going to use two examples of linear frequency transformations. One is the short time Fourier transform, and the other one is the continuous wavelet transforms. What they have in common is that both of these things measure correlation on the signal with a family of templates, right? For the short time Fourier transform, the templates are windows. You're very familiar with Hamming windows and with rectangular windows and triangular windows. So we slide these windows over time, and we modulate these windows over frequency. And because the windows have the same time and frequency duration, they're constant in frequency and in time, then the tile looks like just a rectangular tile, right? Everywhere, time and frequency resolution are the same. Okay, so this means that this is a transform that lets you analyze with the same time and resolution at any point in time or frequency. Now, continuing with this idea of templates and analyzing templates as they correlate to signals, when you do continuous wavelet transform, you also have a template, but now the template is a wavelet. And instead of translating and modulating the template, now you translate it and you expand it or compress it, right? So, this is called dilation, right? Translation and dilation. And there's this relationship between the frequency and the dilation, right? If you have a very long wavelet, then it means it has a narrow frequency representation. And if you have a very short wavelet, that means you have a narrow, a broad frequency representation, right? So you already see this duality that yields towards this behavior here. Long wavelets, good for frequency analysis with good resolution. Short wavelets, great to detect time events quickly, but with bad frequency resolution. And the result is this non-uniform tile, right, where you have very good low frequency resolution, but bad time resolution at lower frequencies, and you have great time resolution at higher frequencies, but bad frequency resolution, all right? And how does this look in real applications? So, when do I use which one? And so let's go back to the tones that I showed you before, and let's look at the side-by-side short time Fourier transform and continuous wavelet transform. So you can see that the short time Fourier transform, I already showed you that it's able to detect all the tones at all the times. But look at the continuous wavelet transform. The continuous wavelet transform doesn't separate the higher frequencies because the continuous wavelet transform doesn't have good resolution at high frequencies, okay? So that's a problem. You really want to detect tonal events at all frequencies, then you're better off with a short time Fourier transform. Now, if I show you this other signal, these are two chirps, right? They are increasing in frequency with a hyperbolic function, and because I plotted them, I created them, I can actually plot the black dotted lines that show me the exact instantaneous frequency where these chirps occur, right? And you can see that the continuous wavelet transform does a great job separating the two chirps. Now, if I look at the short time Fourier transform from the two chirps, the story is very different, right? And I have to separate into two cases. the first case is, okay, let's use a small window so that I have good time resolution. What happens is I cannot detect the lower frequencies. They don't separate because I don't have enough frequency resolution, but I can clearly detect the high frequencies where things are changing fast because I have a good time resolution. Now, on the other hand, if I use a long window, now I have good frequency resolution, but I have bad time resolution. And then you can see that I can separate the lower frequencies, but I cannot look at the events when they change fast in time at the top of the chirp, right? So if you think about this, these two spectrograms together look like what we can see with the continuous wavelet transform in just one plot, right? Good resolution in one domain and good resolution in the other domain, depending on the window sizes. So when you have these fast varying signals that have these transient events, then you're better off using the continuous transform. And if you think about it, transient events, fast varying things are usually of most interest, right? And are things that you want to detect with good resolution because you want to know when fast things happen. Now, one last example, and I was actually talking to you about this on my talk, an electrocardiogram signal has this very interesting behavior where you can actually see all the heartbeats being detected by the continuous wavelet transform, again, fast events that are transient. But interestingly, you can also see these lower frequency lines in the continuous wavelet transform, which are detecting the respiratory motion, which is slow of the patient, right? So the great thing about the continuous wavelet transform is that you can detect low varying frequency events and also the fast varying time events. Okay, so when you're looking for transients, like for example a power surge or a failure, the continuous wavelet transform is the transform to go. And so as a summary, the short time Fourier transform, great for separating tones in all frequencies, and the continuous wavelet transform, great for visualizing transient events and low frequency content. All right, and this takes me to the next topic, which is reassignment. As I told you already, when we use windows or wavelets, we have this smearing effect on the frequency content, right? Very typical, all of you in school have probably heard about scalloping effect or frequency bleeding on the Fourier transform, that it's due to the window side lobes, right? Some frequencies bleed to other, a tonal frequency bleeds to adjacent frequencies, and that's what reassignment tries to fix. I'm not going to go into the very details of it, but reassignment tries to look at the tonal components and reassign the smeared effects into the main tone. And what happens is that you sharpen the transform in a very nice way, okay? Now reassignment, the best reassignment technique the one that we have implemented, and I'll tell you why, is the synchro squeeze transform. And here I show you the wavelet synchro squeeze transform. Side by side, the continuous wavelet transform that failed to localize the tones in frequency, in the higher frequencies, and then the reassigned continuous wavelet transform, where now you can see the frequencies perfectly. And so right now you're thinking, okay, use reassignment all the time. It fixes the problem of the continuous wavelet transform, so now I have everything that is great. And the answer is, you have to be careful. There are certain characteristics in the signals that they need to follow for reassignment to work. Otherwise, you may end up seeing like this very bad effects on the spectrogram that have nothing to do with your signal. So you have to be careful, but if possible, it's a great technique. And I have a great example here of a bat signal. This is an echolocation signal. The bat throws these echoes throws this audio or ultrasound waves and then gets the audio back. And what you can do with reassignment is you can really detect the ridges of the echolocation. You can extract the ridge values, and because reassignment synchro squeezing is invertible, you can create a mask with only the values of the ridge, get everything else set to 0, and then invert it and see the actual waveform shape created by each one of the ridges, right? So it's great. You can actually see the way the ridges in the time frequency content look in time. So very nice technique. We have various functions that do this and extract ridges and everything. So effectively what this is a time frequency filter. So a great application. All right, now the next thing I want to talk about is multi-resolution analysis. So multi-resolution techniques take an input signal and break it into time-varying frequency components of the same time scale as the original signal. There are wavelet techniques and there are also adaptive techniques. But what I'm showing here on the screen is the multi-resolution analysis of a seismograph signal, right? It's just an earthquake. And one of the, on the right, you can see the continuous wavelet transform, and you can see the high energy content on that rectangle. And the great thing about the multi-resolution analysis is that you can relate the frequencies on the continuous wavelet transform to the frequencies over which you have decomposed the signal, right, in the multi-resolution domain. So the great thing is that you can actually see the waveforms in time that caused the high frequency content or the high power content on the time frequency map or the scaleogram, right? So what you're doing when you do multi-resolution analysis is that you're looking at the structure of the signal, but in the same time resolution as the signal itself. Everything is aligned with respect to the signal. Okay, so when you see vibrations in the multi-resolution decomposition, that means that there were some vibrations in the actual signal at the same time. Okay, so it kind of makes the signal naked, and it shows you the internals of the signal, but in the time domain. All right, and there are multiple techniques for multi-resolution, and we have this nice example that shows you a table that teaches you when to use which one, right? It's in our documentation, you can take a look at it, but you know, it's always confusing to figure out which one of the algorithms you need to use. And I want to show you the multi-resolution analysis in action. That's what this next section is mainly about. I already talked to you about why time frequency is important in AI. I told you that it was in the previous talk that it was because of transfer function and feature extraction. And I already told you that it's a key component of the AI workflow. And I'm going to go quickly through these slides because I already covered them in the previous talk. But you know, when you do transfer learning, the idea is that most of the networks that are out there are for image processing. And so if you want to use them with your application for signals, you have to convert them into the time frequency domain so that you can then use transfer learning the way I showed again in the previous talk, right? Where you make this expert network understand your signals or your images, okay? And I already told you also that time frequency transforms can be fed into recurrent neural networks, but I don't know if you caught me in the previous talk, but I was telling you that recurrent neural networks are good for signals, and all of a sudden I put in there a spectrogram. And you probably thought, well, weren't you supposed to put in signals? A spectrogram is an image. Why aren't you using a CNN in here? And the answer is, you can think of time frequency transforms as a channelized version of the signal. So it's just a bunch of time sequences that have been channelized over multiple frequency bins. And if you just change the parameter of the LSTM network to have n number of channels, then you can feed the spectrogram into that LSTM or recurrent neural network. And the beauty of this is that yes, you can use continuous Fourier transform that has the same time resolution as the signal, but you can also use short time Fourier transform that actually windows the signal in a way that reduces the dimensionality of the signal. So you could even reduce dimensionality by reducing the number of windows, okay? And now I know that this is an AA session and that I shouldn't be explaining this too much, but I just want to talk to you really quickly because I want to bring in a concept about deep learning. And so here's a deep network, and the way a deep network works, or deep learning works, is that you feed a signal X in, you get a signal Y out, right? The first step. And you get Y by convolving the signal with all these weights that are inside the network. The next thing you do is you compare X to Y and get this error or cost function or cost value J. And you take a derivative of J and retrofeed back this into the weights and update the weights. I know everybody knows about this, but I want to talk about the derivative part. In MATLAB, you can take all these automated derivatives thanks to a data type called DL array that gives you automated derivatives in the same way that TensorFlow, tensors give you automated derivatives, right? And the reason I'm talking to you about this is because I have been telling you that time frequency transforms should or can be placed in front of the network, but what if I tell you that we can also put them inside of the network, anywhere inside of the network? We can do this now because we have made these transforms differentiable. And when they're differentiable, they can support backpropagation and all sorts of very nice combinations of architectures you can do now thanks to this. We have various of these. We have the short time Fourier transform, the continuous Fourier transform, and the multi-resolution layer available already for use. And I want to show you this example where this was put in action. So we have this health monitoring system, a contactless health monitoring system. When you put a radar in front of a patient to measure all sorts of chest returns from the radar, and simultaneously you measure the electrocardiogram of the system, okay? And so the idea is you have these radar signals and these electrocardiogram counterparts, and can we teach a network to convert the radar signals into ECG signals? And a lot of you may be thinking, you're crazy, look at the radar signals. They have absolutely nothing to do with the electrocardiogram signals. How do you expect a network to do something good here? And yeah, let's start with a quite simple network and feed the raw signals into the network. The green is the ground truth. The red is what we estimated. Pretty bad. Not good at all, right? Yes, you were right. That was crazy to try to do. However, if we make sense of the signals, we may get something better. And this is where multi-resolution analysis comes into the picture. On the top of the plot, I have the ECG signal for reference, and the rest of the plots are the decomposed radar signals. And all of a sudden, around that green area, you see some sort of structure that looks like the ECG, right? We're not that crazy anymore. It kind of looks similar. So we also see this high frequency noise content at the top and this like trend content at the bottom that we can remove and just feed the network with the most important aspects, which are the ones in the green area, right? So these are levels 3, 4, and 5 of the multi-resolution decomposition. And when we do that, it's very simple. We grab our network, we remove the first convolutional layer of the network, and we replace it with our layer, our multi-resolution layer. And we set the parameters such that we only keep levels 3, 4, and 5, the ones in green that I showed you before. And with that, you can see now the ground truth and the results, right? The electrocardiograms appear outside of the network with great results, with great resemblance. This is actually, amazing how you can get a network to work so well by just doing a transformation on the time frequency domain. Now, to finalize, this is another very exciting application. All of you may have taken, the magnitude of a spectrogram and forgotten about the phase, and then maybe wished that you had a way to recover the signal even if you don't have the phase anymore. Right? And so, how do I do that? There are some algorithms out there. One is called Griffin-Lim. It's not that good, but look at this. Because we now have differentiation, we can use a gradient descent approach and start with a signal that is pure noise, get the short time Fourier transform or the continuous Fourier transform, get the error between the magnitude spectrogram that we want to get and the actual magnitude spectrogram, and then do gradient descent and feedback back to update X and do this in an iterative fashion until you get the actual signal. And I'm going to show you this example with this high frequency chirp, right? The black line is the chirp and the blue lines are the noise that I used to initialize this process. And in the beginning, in iteration 1, my estimate is pure noise. I just started. By iteration 25, my estimate starts to look like the chirp. And by about 200 iterations, my chirp is exactly the chirp, or almost exactly the chirp that I had before, with the right phase. Okay, so this is another great use of differentiability, and now you can do this with MATLAB. And so to finalize, I just want to say that there's many apps out there that you can use so that you don't have to write MATLAB code. The MATLAB code gets generated for you once you use the apps. And we also have all these functions to do time frequency analysis, as you may expect, right? We have been working on this all our lives, so they are available. And I want to end with this. We have a time frequency gallery where you can actually look at a table of all of our different time frequency analysis, and then you can see when are they good to use and when they are not good to use, right? We have these recommendations, almost like a menu. So if you want to take a look, they are very useful. And with that, I want to thank you for your attention.